my great pleasure today to introduce Xiao-Ming Liu, who's, for a very brief while still, a postdoc in the Geophysical Lab. Xiao-Ming got her undergraduate degree partially in China and partially at the University of Waterloo, and then got her Ph.D. Early in 2013 from the University of Maryland, and has been a postdoc here ever since. Xiao-Ming will be leaving us this summer to take up a faculty position at the University of North Carolina, Chapel Hill, which is where I was before I came back here. Yep. So I'm very excited for her to go, and they're very fortunate to have her. So today she'll be talking to us about tracing continental weathering using lithium isotopes. And I'll let you take it away. Turn it on.
Yeah, thank you, Lara, for this very nice introduction. Thank you, everyone, for coming. Okay, so let's just start it. So today I would like to talk to you about using my favorite isotopic system, lithium isotope, to study continental weathering. Okay, let's start first. Let me show you a very nice cartoon about how the continental crust is generated now. We see that the continental crust is usually generated at the arc settings, where the existing continental crust is colliding with oceanic crust, and then we have melt generated. Then we have either eruption of volcanoes or plutonic intrusions generating the new continental crust. So why do we care about continental weathering, right? There is a so-called crustal composition paradox. We know that the magma that generated the current day continental crust is basaltic. At least the majority is at these convergence margins. However, the juvenile the bulk continental crust, the one that I'm standing on and you are sitting on today, is andesitic in composition. So just show you what a typical basalt looks like, a rock basalt, and andesite looks like. So they are actually different in terms of silicon content, right? So the more, we call it more felsic, it's more silicon enriched, more mafic, meaning more basaltic composition. So this discrepancy between the building block and the building, right, is usually referred as crustal composition paradox. So many hypotheses has been proposed to solve this crustal composition paradox, including involved melt addition in a hotter alkene, because the alkene may have higher degree of partial melting. We have more felsic crust at that time. So the juvenile crust may be not entirely basaltic as it is today. Also, there is an idea of recycling of the lower ultramafic and mafic lower crust, because the lower crust is more mafic in composition. So by detaching from the continents, we get the bulk crust to be more andesitic. And also there's a new idea of relamination followed by subduction of more felsic crust onto the continents. So we could have more felsic crust that way. And of course, the focus of today's talk, I'm not going to talk about three other mechanisms. I would like to pay more attention to chemical weathering as one mechanism to changing the crustal composition and mass. So this is a very childish cartoon. Oh, I drew it. So it's not to scale, of course. Okay, but this one just gave you an idea of what I'm talking about chemical weathering. Chemical weathering preferentially removes soluble elements such as lithium, sodium, magnesium, and calcium, and remove them into the oceans. So that leaves the continental crust to be more silicon-rich, right? So that's one possible mechanism. However, traditionally in the high-temperature geochemistry community, people think this is not an important mechanism because this is only a top-down process, right? It's only up to the upper continental crust, couple hundred meters distance, right? However, how important is important, right? We need a way to quantify. So we did Steve is not here, I guess. So but I don't want to put the rest of you into sleep. So I don't show you the mass balance model. So we actually did a mass balance model based on lithium isotope to look at the input of the continental crust and the output to quantify how much of the mass is lost due to chemical weathering from the juvenile crust. So I'm not going to show you the mass balance. You can check our papers a couple years ago, and you just have to believe me. It's important because it's 15% is our minimum estimate. So that's another motivation why we need to care about continental weathering, right? Okay. Another important reason is we know that tectonic uplift is increasing the continental erosion, right? And also continental weathering, especially continental silicate weathering, is the net output for the CO2 in the atmosphere. As you all know, the CO2 is important in terms of regulating the climate, at least in this geological scale we are talking about. We're not talking about the future climate change. Anyway, so continental weathering is actually a natural connection for the tectonics and also the climate change. So it's an important link we need to investigate more. Okay, so I'm a geochemist. I like to look at the periodic tables every day. And we want to find the best system to study the geological processes we want to study. In our case, is continental weathering. So lithium is great in terms of continental weathering, not only because it's important in our laptop and phones as batteries, but also this. Have you drink this very interesting drink, 7-Up? This is probably very first commercial of the 7-Up. So I actually speculate why this drink is called 7-Up. You know, before 1950s, they add lithium citrate in the 7-Up. And lithium is a known mood-modulating drug. Actually, nowadays, we take lithium to treat bipolar disorders and etc. So it can potentially make you happy, as this commercial says. So nothing does it like 7-Up with a happy baby. Probably people grow up before 1950s are happier than us. Now we don't have this good stuff in there. Okay, so if being happy is not enough reason, we have more reasons for using lithium. Lithium has two stable isotopes, lithium-6 and lithium-7. As you see, the 7 is more than 90%. It's a majority. Lithium diffuses really fast, and also lithium is soluble. So it makes it very well in terms of transportation process during fluid-rock interaction. And also because lithium has only one redox state, so it doesn't get into very complex redox reactions, which is good in terms of weathering processes. As you already noticed, probably, lithium as a very light element. Therefore, the two isotopes, 6 and 7, has a relatively large mass difference between 6 and 7. Right? So it can give rise to very large isotopic fractionation potentials, the mass-dependent fractionation. And also, the also bonus point is we know that lithium has relatively limited fractionation in high-temperature processes such as mantle partial melting. So it's great for tracing low-temperature fluid-rock interactions, such as weathering. Okay, so this one shows you a diagram of what a typical product weathering, a clay mineral, looks like. So this is a kaolinite mineral structure. Lithium likes to replace the aluminum in the octahedral structure. Versus in waters, lithium likes to bump with 4 different water molecules to form this tetrahedral structure. So this is actually known from very fractionation mechanism theory that we know the heavy isotope prefers the higher bonding energy site and usually corresponds to low coordination number, right? So that means the heavy lithium likes to go into the tetrahedrally coordinated water, and then the light isotope likes to be in the octahedrally site of the secondary minerals, such as a clay or iron aluminum hydroxides. This has been well established by many observations as well as laboratory experiments. So that's the fundamental fractionation we will use in tracing weathering processes. Oh, by the way, if you have any questions, you can ask in the middle. Okay, hopefully by now you're so excited you want to know how do we do it, right? how do we measure lithium in the laboratory, right? As a geochemist, we work with geologists. Also, some of us are geologists. So we go out, we pick up the samples, either in forms of rock or water. Then we, for the rocks, we cut them into powders in the end, and water, we evaporate the water, the majority, and then leaving the lithium in the solution. So then we do laboratory experiments for sample dissolution, where we use very strong acids like hydrofluoric, hydrochloric, and all the very dangerous acids to dissolve the rock or water sample, anything you want, basically. And then we can go through, for isotopic study, we need to purify the solution because we only want the isotopic system of interest, in this case lithium. So we set up a chemical exchange chromatography to get rid of other elements that we don't want. But basically, we only have lithium solutions in the end. So this is a very laborious process, so it needs a lot of crying time in the lab, or happy time in case of lithium, right? So we have then taking the purified solution into this multi-collector ICP-MS. So it's a plasma source mass spectrometer. This is actually the closest thing, I think, on Earth you can get to the surface of the sun because the plasma temperature is 8,000 degrees C up to. So you basically, at that temperature, you can ionize everything. So we put through the purified lithium solution, go through electrostatic analyzer, and then the big magnet, where you can separate two isotopes, lithium-6 and 7, in terms of their mass difference. And then at the end, it goes to a collector. It's actually basically big resistors. Right? You have current hit the resistor, then you get the voltage reading. That's how we get the isotopic ratios. As other stable isotope systems, like carbon and oxygen, we express isotopic fractionation using the standard delta notation. So it's lithium 6 to 7 in the samples divided by the 6 to 7 ratio, 7 to 6 ratio, always heavy versus light. And subtract 1 times 1,000, so we can get a big number to work with, not 0.000 something, right? Okay, so now you're going back to this cartoon, we can see how does lithium looks like in weathering-related reservoirs. We have relatively homogeneous mantle composition. It's about 4 plus minus 2. The upper Continental crust is a little bit light because the fractionation I told you before, right? The formation of secondary minerals like clays prefers the light isotope. So the upper Continental crust especially has been through weathering. So we have the light values. And then I would like to point out the water, they interact with the rock, right? Must have heavy value to make the mass balance work. And the seawater additionally have even heavier value because there is additional orthogenic clays formation on the seafloor. So we have further fractionation from the rivers, but that's not a topic I want to talk about now. So if you haven't looked at this, I want to show you a more pronounced histograph. The problem here is we have average upper Continental crust, very homogeneous, average basalt, relatively homogeneous. Oh, boom, you see there is a huge variation for rivers that even only draining basalt. It's a single lithology small river. They have like 30 per mil fractionation, right? It's one of the big questions that motivate my study is what controls lithium isotopic fractionation during weathering? Why the rivers has such a wide variation in terms of isotopic composition, right? So, and there's another one. There's a paper, interesting paper published a couple of years ago, using foraminifera, acute fossil, as a paleo oceanic proxy to look at the lithium isotopic variation through time, right? So basically, what they found is through the Cenozoic, there is 8 to 9 per mil increase in terms of delta lithium from the Cenozoic to now. So what this means, right? So is that meaning we have more weathering? Because lithium is really low content, has really low content in the carbonates, right? And is very enriched in the silicates. So they invoking a proxy for secular evolution of the continental silicate weathering, especially because lithium is not much in the carbonate. However, if we consider a mass balance in current seawater, we have lithium, and then we have two important input, which is hydrothermal fluid as well as river water, versus also the river water is a continental weathering. And also we have output for the seawater, lithium in the seawater is actually through the oxygenic clay formation and also basalt alteration under the seafloor, both of them taking lithium from the seawater. So it's actually not very easy actually to say. However, I would say the hydrothermal fluid is, hydrothermal activity is not probably likely to change too much within the 60 million years. And exactly how it changed probably is not well known. And also the formation of oxygenic clays and the basalt alteration, the mechanism at least not change. So the most variable part of this is actually river water. As I showed you before, river water shows a large range of lithium isotopic composition. So it's more likely the seawater reflecting the continental weathering, the riverine part, right? So that's actually helped us to connect between the climate and the tectonic influence, because both of them are important in terms of changing the continental weathering patterns. Okay. So this leads us to look at the questions, okay, to address. As I emphasized before, we want to know what controls lithium isotopic fractionation during weathering. So there's two kind of study we can do. One is we study the weathering profiles, which is left over from the weathering process. One is from the rivers, which is taking way into the oceans. And also, actually, I already emphasized to what degree chemical weathering has changed the composition of the continental crust is also important question. And also, we have particularly good proxies to study the secular evolution of the continental silicate weathering using lithium isotope. We want to test if this tracer is a good one. So this one just gives you a very simple idea, right? Since the building block of the continental crust is originally basalt, so we want to study basalt weathering. So this is a picture taken from the Columbia River basalt. Actually, this is people doing rock climbing in those big columns, actually. So actually, if you think anything on the surface of Earth, it's actually been through weathering. So this is a very simple cartoon. A rock, basalt, sitting on the surface of the Earth, right? Then we have precipitation in forms of rain or snow interact with the rock, fresh rocks on Earth's surface. Then they can produce soils and water, basically weathered rocks versus water. The rocks, the weathered rock or soil or weathering profile, whatever you call it, staying on the surface of the Earth, and then the water's going away. But yeah, some of the soil can go with as a suspended load into the river as well. But that's another complication. In the meantime, actually, this is not, I want to emphasize, this is not open system behavior, because you may have a dust, aeolian dust component from outside of the system, right? So, okay, so we will focusing on the weathering profile part to address the issues of what actually fundamentally control the lithium isotopic fractionation during weathering. I want to show you some previous study, just summarize. We both have experimental study and natural observation that no lithium fractionation actually occurs during the primary mineral dissolution without the secondary mineral formation, right? And then we have fractionation of lithium in the secondary mineral formation. As I showed you, the lower lithium likes to stay in the clays or iron aluminum hydroxide. So they produce low lithium signature in the minerals, secondary minerals. Okay. So we know that. And then we still want to have a systematic study to look at both rivers, groundwater, as well as the weathering profile, fresh rock from the same system. That's why we go to the Columbia River basalt, because we need a lot of basalt to look at the weathering. So that's a natural place we can find a lot of basalt. So the Columbia River basalt system is located in the Washington state and also Oregon and a part of the Idaho. As you can see, it's a large igneous province, and it was erupted in about 16 million years ago. Because the basalt showing in this gray here are widespread and also well studied, so we can look at the weathering because we know their appearance pretty well. And also, we have a bonus in terms of looking at the weathering system here, because the rise of the cascade having the mountain shadow effect, making the climates to be different in the west and in the east. So we have more precipitation, more than about 2,000 millimeter per year in the west, and then we have pretty dry, less than 300 millimeter per year in the eastern part of the Columbia River. So we can look at the weathering from different climatic conditions. Okay, so we, as I promised, we will study some weathered rocks, right? So we got some drill cores. They are already bauxites. So what is a bauxite? They are actually extremely weathering product. Looks like this. Very, very aluminum oxide and also hydroxide rich. Basically, made of XRD shows majority of them are made of gibbsite and hematite, with some a little bit kaolinite or other clays and iron hydroxides. So those two drill cores are from the west of the cascade. So they are from the wet weathering, right? And they are from the drill cores about 10 meters in length. What's interesting is we found cores on top of the 3 to 5 meters of both the weathering profiles. So cores, as you know, is not supposed to be the primary mineral for basalt, right? So that's our first hint if something is going on. And also, if people study weathering processes, we like to use this term CIA, not the agency, but the chemical index of alteration. So this is basically aluminum content versus some alkali element to indicate how much of the rock has been altered due to fluid-rock interaction, right? The more aluminum you have, the more weathering has occurred because you lost all those mobile elements, soluble elements. As you can see, I mean, all those boxes are the bauxites, the weathered, very crappy material, and then those bars indicate the parent material, which is the basalt. And for both the two profiles, both Cowles and then one Columbia, so that's two different weathering profiles I showed you before. So all of them showed a very homogeneous parent 40, and then the bauxite showing 99. So 100, as you can see from this equation, is the highest you can get, right? So 99 is we say, is extreme weathering. But as I want to point out, we cannot distinguish all those samples in the bauxite because they all look the same, all extreme weathering. So we did this lithium study to look at how they behave during this extreme weathering, right? And it's the same profile for both Collis and Columbia, where we have the parents in the bars, characterizing the uncertainties in the bar. And also we do the delta lithium. As I showed you, the definition is the same as other stable isotopes. So first of all, we see there is a depletion of lithium content, right, in the bauxite compared to the parent. And then we have a systematic kind of decrease for the isotopic composition, right? So this we can try to explain, right? So the first depletion we can easily explain because lithium is a soluble element, right? So it's of course lost during weathering. However, the top enrichment is not known. So for the isotopic value, as I showed you before, the fundamental fractionation of lithium isotope is the secondary minerals, or like clays or iron oxide, prefers the light lithium. So it's not surprising we have a sort of upward rising, decreasing delta lithium with depths because it gets more weathered on the surface. So, but then the enrichment here is not explained. it could be due to aeolian dust component, and this one is due to secondary mineral formation. So we can explain this all, but the aeolian dust, we cannot be for sure because lithium could be behaving non-homogeneously. So we want to do a more definitive study focusing on neodymium isotope, because neodymium isotope is a good tracer to study the source. So we can analyze all the parent material and also the bauxites in those diamonds, and also we analyze the dust sample we collected from both west and east sides of the Columbia River. We can see clearly, first of all, it's very surprising because sometimes people claim that neodymium is not mobile during weathering. But in this extreme weathering case, the neodymium is actually depleted in those bauxites. So the parents are showing in those bars, right? The second important point is we have seen the dust having less radiogenic signature, as well as those top 3 samples from both profiles showing similar less radiogenic signature as the dust. And also the bottom profile showing similar signature compared to the parent, right? So that's actually very good because those samples corresponds to the ones that we did the XRD. So those are having course in their mineralogy. So that's a more definitive proof that those are likely from the aeolian dust component for those top samples, right? Where we see the lithium enrichment as well. Right, so just to want to mention this is important when we talk about the lithium isotopic fractionation in the weathering profiles. Okay, so just the main point, I would like to show you, hopefully you're convinced, both leaching, secondary mineral formation, as well as the aeolian dust addition controls the lithium isotopic behavior because weathering is an open and a dynamic system. So lithium can have a capability to trace both the origin and the evolution processes. So that's good.
Is the grain size of the quartz consistent with it being dust deposited?
Yeah, well, it's actually harder to see. We didn't see it. It's all the material is all crappy, so we didn't do the thin section analysis. So we had to crush the whole samples to powders. Go to the powder XRD, so it's hard to know the grain size curve. Yeah. Right.
Did you measure the lithium isotopic composition of the dust?
Yes, we did.
What was it consistent with? Did you show that here?
Oh yeah, I probably didn't. Well, yeah, it's lower, so it's close to the upper Continental crust. So it's around, one of them is -1, one of them is +1. So it's 0 ± 2 within the upper crust range. Good point. I didn't put it up. Good. So you're ready to get a little bit wet after this. So, and then the second part, I would like to address the what controls lithium isotopic fractionation, looking at the rivers and groundwaters. So that's the wet part. Okay, so we know what controls lithium, sort of. Before that, we want to give you an introduction of this definition, weathering intensity. So people talk about this all the time. It's basically reflect the fraction of the total material available for dissolution that has already been previously chemically altered, right? So the higher the weathering intensity, meaning the sample already been through all the weathering. However, we have 2 different schools of what controls lithium in rivers in the literature, because some claim that the high dose lithium is usually correlated to low chemical weathering intensity terrain, where they found there's high dose lithium values in some Andes rivers that drain in Andes in the Amazon. And also some claim that high dose lithium may reflect the low silicate weathering rate, right? This intensity is an accumulated effect, but rate has the time component. It basically correlates with the flux. So we want to look at the lithium isotopic behavior to see what actually controls the lithium behavior by a small rivers. So this is our advantage of doing this kind of study because, as you know, we're focusing on the Columbia River basalt system. We already characterized the weathering profiles as well as the appearance, the potential dust component, and also we can keep the catchment lithology the same, right? So the catchment lithology is the important factor in influencing the what's dissolved in the river. So if we keep everything is basalt, so we get rid of other factors influencing lithium behavior. And also climate may be important because there is different precipitation and temperature may have different lithium isotopic behavior. And also we would like to address seasonal variations, right? If you take, you never, there's a saying, you never walking the same river twice, right? So there's always seasonal variations possibility. So this kind of motivate us to try to invest rivers and groundwaters in the single lithology catchment, which is the Columbia River basalt, where you can see it here. So we did a geological map of basalt exposure, which is the light green in this area, and then on top of a hydraulic map. So those are the positions we took samples. So all the orange circles are the rivers, or maybe we should call them streams. As you will see, those are only meters cross. Those are not real big rivers. Those are small rivers. The point is they are all weather the light basalt. So we don't want to have other components. And also the triangles are some groundwaters we took in the basaltic terrain. So we also do this in two different campaigns. We do it in summer, very nice, and kind of cold late winter as well, to sample the same streams and groundwaters. Just want to give you an idea, since we are not there, give you an idea of the Pacific Northwest, the climate, right? It's actually very interesting. For the summer, it's all dry, and the late winter, the west part of the Cascade is actually very wet. So the precipitation was higher. So remember that. So that's our study area. That's the Columbia River basalt area. So just keep that in mind. So there's some fun. Always fun to have some cute photos. That's a very nice summer photo. In the west, you will see some soil development, red soil, and then in the west, there's like hundreds meters of basalt. So a lot of basalt in the dry eastern area. So we took some river samples as well in relatively west and also the east samples, and also in the cold winter where we have snows. Okay, now we look at the data because we did the two different seasons. One is called winter, one is summer. So we plotted winter dust lithium versus summer dust lithium. And also because the locality, we have the western and eastern river. So the western river are shown in the green and eastern are the yellow. The first thing you can see, no matter in summer or winter, there is a large range for the dust lithium value, right? Even in those very small streams that we think is only weathered basalt. So that's surprising. And the other thing is if you look at this long time, enough, like me probably, you can see there is a 1-to-1 line on those eastern rivers. What falls on this line means there is a same, there's no variation between the summer and the winter dust lithium, right? And all the western rivers showing the heavier values in the summer. So that's another interesting observation. But if you do the math correctly, I done 10 rivers twice, so I only showed like here only 9 points, right? So there is only one off, so that's the honest point, right? So in the sampling season, actually we saw cow poos in the stream, and also because we did all the major cation and anion analysis, we found there is a huge amount of chlorine and sulfide in those waters. So there is more possibly fertilizer contamination or I don't know, cow pagenic contamination. So we don't want to talk about that too much. Okay. Anyway, So if you look at the whole behavior for both summer and winter, for the streams shown in those circles, and also the groundwaters showing in those triangles, I would like to mention that there are some deep groundwaters that actually meaning a couple hundred meters depth into the basalt. So actually their residence time is probably thousands of years. So they are actually not reflecting what's going on now. So that's why you probably have to look at it in this grade. But anyway, if you look at this behavior of lithium concentration versus delta lithium, by the way, we would like to normalize it to sodium is because both lithium and sodium are soluble elements, but have similar solubility. But lithium prefers goes into the clays, not sodium, not much. So this is an indicator of how much of additional weathering going on in the rivers that we like to use. Anyway, if you ignore, there's kind of statistically 4 samples, but it's very hard to get groundwater data, right? Some of them we actually went to bathroom faucet. We know that there is a deep groundwater wall. But anyway, so despite this, there is one deep groundwater that will follow. Majority of the streams actually having heavier values compared to the groundwater, right? So that's our first observation. And also there seem to be a trend of this increasing delta lithium with lower lithium sodium ratio, where previous people thinking there was maybe a mixing of 2 different weathering regime, meaning one of them is probably formed by secondary minerals and the other one is probably by manganese oxide or something. But we were trying to explore this by some models. So this I'd like to give my collaborator Chris Warner a credit. He did basically this reactive-transport model by looking at how the pure water plus some CO2 going through a Columbia River basalt rock. We gave it some proxy. So the water going through with some residence time and then coming out. So this part is actually simulating what's going on in the groundwater, right, subsurface. And then this groundwater comes out and then mixed with some fresh water. This part is simulating what's going on in the precipitation, right, whether rain or snow. And then this what's going on in the rivers. We try to simulate that. So we did these 2 individual simulation, both for the subsurface, groundwater, and also the river simulation. For the source of lithium, we use the glassy basalt because lithium is relatively incompatible element, so it goes to the glass for those high temperature geochemists. And lithium is bearing actually in the secondary minerals. We assume it's in the kaolinite or hematite. Right? Then we can look at the simulation result for 2 end members where we assume a low lithium concentration for ppm and then a high lithium concentration is 20 ppm for the basalt because we actually measured the basalt, so we know that's the range we observed. So if you can see, this part is for the subsurface, which is the groundwater, and this is the river, right? So in the groundwater with longer residence time, it's not surprising we release more lithium and also silicate into the rivers, right? So that's, into the groundwater, so that's not surprising. However, because there is a mixing of fresh waters in the river, so we see the decreasing behavior for both lithium and silicate content in those simulations. But if you look at the delta lithium part, it's actually not too much difference between the 2 different starting composition. So no matter if it's 4 ppm lithium or 20 ppm lithium in the basalt, all those behavior are the same, right? So all the rivers show an slight increase in the subsurface, and then a huge increase in the rivers, right? So if you remember, like my previous diagram is an opposite correlation between the delta lithium and the lithium concentration. Actually, that's exactly what we observed. And we would like to point out there is a very delta lithium increase with increasing residence time. So we would like to argue it's actually the residence time, the hydraulic process, controls the lithium isotopic fractionation in the rivers. So you can have the huge range. And also the other important finding for this simulation is we we see there is additional weathering going on in the rivers, right? So that's why we can explain why our river samples have higher dust lithium compared to the groundwaters. So all the rivers should have higher values. No questions? Clear as mud? Okay. So if you're not so convinced, we try to really plot this to what we observe. So all those pink squares are the observations for both seasons, as well as rivers and groundwaters. So those are the two lines that simulating the two end member of the basalt we put in. So it seems to work out pretty well with increasing residence time. We have higher fractionation. And also we try to compile some data from literature where we observe the Atlantic rivers and also a river from the Azores where people only see the weather of basalt, right? And this seems to have the similar trend in terms of lithium-sodium ratio versus dust lithium. So we would like to argue that the residence time controls the dust lithium and lithium-sodium ratio behavior is reflecting fundamentally the residence time. In another word, it's fluid rock interaction, how long the rock has been influenced by the water, right? So this correlation seems to be a worldwide effect, not only small study. Okay.
Why do the pink points look different on the two plots?
Because I think because let me see. I think because the scale is different. So there were some over there. It didn't show over there.
Okay, I'm just
Right.
trying to compare by eye.
Right, and also maybe this. I think this one I already got rid of the groundwaters. This one has the groundwaters. Yeah, I think. Yeah. Too many colors. Sorry. Okay, so the bottom line is I just want to show you what controls dust lithium in rivers. We think it's the residence time. So not the fractionation factors between two different minerals versus the water or weathering regime argument. So anyway, so this is another way to emphasize. I guess the seasonal variation also we saw is another good example why the residence time is important. Remember I showed you the delta lithium in the summer is actually higher compared to the winter, right? The summer, because the western has a lot of western of the Cascade, the western has a lot of precipitation, and then you have more residence time between the water and also the weathering profile of the soil. That's why you could have heavier dust lithium. So that actually goes well with our residence time argument. And also the other important thing is there's an additional lithium fractionation in the rivers, because we assume there is additional reaction between the suspended load and also the water, right? That's why you have fresh kind of small rock chips or small particles in the rivers, and then they keep reacting with water as they transport along. So that's why we got additional lithium fractionation in rivers. That's actually what's observed in nature as well. So we would like to propose there's possibly a good proxy for the dust lithium versus the lithium sodium. They're actually reflecting the degree of the fluid rock interaction. So by plotting where on the line, we can try to figure out how much of the weathering has going on, right? So that's another one. Oh, okay. So one more thing we want to, as I originally showed you this very intriguing study where we see an increase of dust lithium through the cenozoic. So now we would like to go back to try to explain a little bit more, because we know that this increase has to require a change in dissolved river in dust lithium. So we are kind of ignoring the hydrothermal input change and also the orthogenic clays output, right? So because this study showed we need to have a riverine change to have this dramatic increase in terms of marine dust lithium values. So collaborating with Chris Warner, we have done a global scale simulation where we look at the weathering from the granite, because that's the average composition of the upper continental crust. So this one, I just show you one simulation result that maybe useful for explaining why we have this large increase. Because if we do a relatively small suspended load, so this part is also the river, and that's a large suspended load. So if we have increased the weathering intensity, meaning we have a lot of fresh materials to weather, we could generate a much larger delta lithium. So this actually goes with the rise of the Himalayas, because there is a mountain building, mountain uplift can cause more erosion, which generated higher suspended material in the rivers. We can have higher delta lithium. So that's still one of the reasons to explain. So the tectonic uplifts cause increased weathering to explain the Mizora and Folic diagram here. So to conclude, I hope I convinced you that the degree of fluid rock interaction or the residence time is very important in terms of control lithium isotopic behavior, as well as secondary mineral formation and aeolian dust, because the weathering is an open and dynamic system. It's not a closed system, so you need to be always careful with additional dust. And this one I didn't explore, but we already showed there is at least 50% of the total juvenile crust mass has been lost due to weathering. That's like an accumulated effect. It's over the history, the Earth's history. So it's doesn't have a flux component. So, and also yes, I hopefully by now you are still awake, and also know lithium is a good proxy for secular evolution of the continental silicate weathering. Okay. With that, I would like to thank all my collaborators in the lithium work, as well as my mentors in the Geophysical Lab for the postdoc fellowship, Bob and Art, and others for inspiring for doing this part of the study. And I'm grateful for all of you to come in a nice summer day. Okay, thank you.
All right, we have time for a few questions.
So, very nice talk. I was going to ask you about the river, but you explained that. So it's a combination of the mechanical combined with the chemical gives you the pump up. So another question I would ask is, the carbonation contracts have been very extensively altered, and the question's always been, how do you measure how extensive? Because you just have residue of that. Is there any way you could use lithium isotopes, you think, to make some estimate about sort of what the water rock ratios might have been during the parent body evolution of a now say C1 type chondrite?
Right. Yeah, that's a great question, but depending on the alteration temperature though.
Right.
So if it was higher temperature, then the fractionation is not pronounced.
Right.
So I don't know what's it's more hydrothermal temperature or surface temperature. That's another question. Because if it's hydrothermal temperature, then the fractionation is more small. As you know, it's negatively correlated with temperature. Right. That's why I switched my study to low temperature for lithium, because we can see big fractionation. Yeah. That's a good point. We should think about that.
I have two kinds of questions. One has to do with the chemical weathering. Did you measure both the dissolved load and the suspended load in the same samples?
Right. Yeah.
Of
So
lithium isotopes and concentration.
right. Yeah. So we measured where we can, because it's the first time to do this. You know, the rivers, as I showed you, probably it's not very clear, but those are really pristine rivers. Those are pristine streams, actually. So those are having really low suspended components. So we filter them. We use a filter on site using a peristaltic pump to filter the material. So we do have a filter size of 0.2 micron. So anything lower than that we classify as dissolved. And then there are some particles on the filter. I dissolve them and then analyze the suspended part. So the suspended part actually having slightly lower value.
Did you show those data?
I didn't show the suspended part.
Because you make statements about the suspended load, but I don't remember seeing any suspended load
Right.
data. Okay.
Yeah, that's a good point, because there is only half of them I can got the suspended load, because it's pretty clear river. There's not much of suspended load. So we run the filter for a long time, but still there's.
So the other type of question I would wonder about, if fluid rock interactions are important at ambient have you thought about
Right.
metamorphic processes and hydrothermal processes?
Yeah, so metamorphism is important in terms of lithium content, not much in the isotopic composition. So people already did the study from the green schist metamorphism, very low, metamorphism to like granulite phases metamorphism. So the dust lithium actually in the rock doesn't change. So because it's a high temperature fractionation. That's actually go back to George's question. If you have high temperature like more than 200 degrees C, the fractionation is small. In terms of our current analytical precision, we cannot distinguish that. So if you have high temperature fluid coming through, and then most likely the fluid is just getting out the lithium, and then the residual rock is still having the same isotopic signature as the with the same with the parent. So it doesn't change. But it does deplete a lot of lithium, because lithium is very mobile element. Yeah. So it definitely has a great effect on lithium concentration. Right. So
Additional questions, or a few hands here, but maybe you already answered a lot of these questions. All right, well,
yeah,
here-
it's time for lunch.
Yeah, no more questions. Thank you all again for
Thank you.
coming.